Okay, so welcome back to another video. So here I have the definite integral of -1/2 to 1/2 up the square root of x squared plus 1 plus the square root of x to the power 4 plus x squared plus 1 dx. This is a special type of integral because this is actually one of the 5 integrals presented in the final round of the 2023 MIT Integration Bee. So you could probably find videos or solutions out there on someone's perspective / take on how they would actually get to the answer, which is actually going to be the same thing presented here, of course, but this is going to be a different approach how we're doing this. So we can actually, to give away like the steps and outline how we're doing this, we want to do this such that we set this to some sort of constant, then perform some sort of algebra, specifically utilizing systems of equations that we actually add and subtract different equations in order to get a specific constant we want, just so we can have our current integrand reduced into something a little bit simpler into that case. Then afterwards, it actually relies on a bunch of calculus techniques. Well, for one, usually some substitutions, use substitution specifically. And another way we'll be utilizing that is, utilizing some trig identity. Specifically, we'll be actually using some hyperbolic trig identity / functions to do the substitution. And then it will come down to the answer that, of course, you can just look this up yourself. That's come exactly how it's supposed to be. So with that, why don't we actually just jump right in? So we'll set our integrand. So it's the square root of x squared plus 1 plus the square root of x to the power 4 plus x squared plus 1. We're going to set that to the following constant. We're going to let that equal the square root of a and then plus the square root of b. So we have to find our constants a and b to help reduce this down easier. So with that out of the way, let's actually perform some algebra and take the square root of both sides. So I have take the square of both sides. Apologies, x squared plus 1 and then plus the square root of x to the power 4 plus x squared plus 1. So that means if I actually just expand this out, so square root of a plus square root of b, then quantity squared, so using that expansion of the FOIL method, we actually get that this is just a plus the 2 times the square root of a times b, and then plus b. All right, so with that out of the way, so why don't we actually set some constants into each other? So to make things a little bit better, we have a square root with a square root, so why don't we set that equal to each other, and then a plus b set to x squared plus a. So a plus b is going to equal to x squared plus 1, and then another equation, that means we'll set that 2 times square root of a times b, we'll let that equal the square root of x to the power 4 plus x squared, and then plus 1. So with that in mind, now let's actually perform a little bit of some systems of equations, usually specifically we're actually going to take one of the equations and then utilize the arithmetic behind it. Let me actually just label this as equation number 1 and then equation number 2 over here. So what we're going to do is let's actually take equation number 1 and we're actually going to square that. So let's actually put with equation 1, we're going to square that. So I have equation number 1 squared, so that means now this is going to be, so expand this out, so I have a squared plus 2 times a times b, and then plus b squared. So that means on the opposite side, square that, so I mean I have x to the power 4, and then add this with 2 times x squared, and then add this with just 1, all right? So let's do the same thing for equation number 2. We're going to square that. So now that means I have, this is going to be 4 times a times b, and set this equal to x to the power 4 and then plus x squared and then plus 1, and just getting rid of the radical. So now with this in mind, so why don't we actually now take these 2 equations and subtract each other. So if I subtract that, then that means now this is just going to be a squared and then minus 2 times a times b, and then plus b squared, and then set that this is going to be, so subtract here, this is actually going to be x squared. And then another thing to reduce this down is that a squared minus 2ab plus b squared, we can simply reduce this to say this is just a subtract b and then quantity square. So let me just also write that to set this equal to x squared as well. So now we can actually go into further detail to say that we can actually take the square root of both sides over here and say that this is actually just a minus b is just equal to just x. So we have a minus b equals x. So let me just write this on the top because it equals x. And then we're going to go back to equation number 1. So equation number 1, we set that this is a plus b. So a plus b is going to equal x squared plus a. So what I really should have done is I should have wrote this on the top and then write this on the bottom. Because what's next is that we're actually gonna, again, do a little bit of, we're not a little bit, but we're actually going to subtract the equations. So if I subtract over here, so that means what I have is that this is gonna be, so this is negative 2b, and then set this equal to x. So when we first write this as x and then subtract, x, subtract x squared, and then minus 1. Then if I just want to get rid of the negative over here, so I have this is just 2b and then c equal to, so let me set the leading coefficient. So the leading degree x squared and then minus x and then plus 1. Okay, and so now just divide the 2 to both sides. So I have that b is going to equal to 1/2 and then multiplied by x squared minus x plus 1. Okay, and so that's our b constant that's going to go back into here, but we still have to solve for what a is. So let's actually now put b back into this equation over here, a minus b equals x. So now let me just put the asterisk over here. So substitute back into this equation over here. So now I have now a, and then everything is subtraction. So let me actually also distribute the 1/2 into everything. So I have x squared divided by 2, and then plus x divided by 2, and then minus 1/2. And that's still set to equal to x. So now really all we have to do is just get a by itself. So that means a, so just put all the terms on the opposite side. So now I have just so, and also factor out the 1/2 too, since everything is in the 1/2 you can factor out. So I have 1/2 and then multiply by x squared and then plus x and then add this with 1. Okay, so we have our a and our b. So therefore the integrand, so that means to reiterate all this, so the square root of x squared plus 1 plus the square root of x to the power 4 plus x squared plus 1, we can just simply write this to say that this is the same thing as the square root of, so x squared plus x plus 1 divided by 2, and then add this with the square root of x squared minus x, and then plus 1 divided by 2. So that's now the integral we're dealing with. So I is going to be what the integral we were actually dealing with. So I is going to equal to positive 1/2 or negative 1/2 to positive 1/2 of the square root of x squared plus x plus 1 divided by 2, and then plus the square root of x squared plus or minus x and then plus 1 divided by 2, then dx. So this is what we're dealing with right now. So I'm going to get rid of everything right here, and then we can actually continue further with now doing the actual calculus. Okay, so to reiterate, so far we actually did all that algebra utilizing the systems of equations techniques to get that we can reduce our original integral into this new simplified integral, square root of x squared plus 1 divided by 2, and then plus the square root of x squared minus x plus 1 divided by 2. And another thing, you want to jump another step, we can actually factor out the square root of 2 once you actually, take that outside the radical and then put that outside. So now I have 1 divided by the square root of 2 and then multiply by all that, so negative 1/2, then to positive 1/2 of now the square root of x squared plus x plus 1, and then plus the square root of x squared minus x plus 1, and then dx. So that's what we're dealing with. So how can we continue such integral, maybe a little looking complex at first? So why don't we actually take another step and actually just complete the square for both our radicals inside. So jumping the gun ahead, if you do all this, if you apply that, so that means I have 1 divided by the square root of 2, multiplied by the integral, 1/2, and negative 1/2 on over here. So now what we have now is that this is going to be the square root of x plus 1/2 quantity square, and then add this with 3 divided by 4, and then you just do the same thing for the other one. It's still the same thing. Similarly, except we have a minus symbol. So this is going to be x minus 1/2 quantity square, and then plus 3 over 4, and then dx. All right. So with that being the case, so now we can let's actually perform a u substitution to make things a little simpler here. And the thing is that we're actually, of course, doing some linearity, so we can actually split this into 2 integrals. So I have a 1 divided by square root of 2 for an integral of this, and add this with 1 divided square root of 2 for the integral of this on the same bound too. So what we're doing is a u sub, but it'd be a little bit repetitive to do the same thing twice, but the argument still follows. So I'm actually going to do for one step, and then just go on to say that you can actually apply the same steps and you'll get the similar results in that fashion. So we're actually just going to be looking at this integral over here. So with that being the case, so let me actually just mark an asterisk on what we're dealing with. So 1 divided by square root of 2, and then so 1/2 or negative 1/2, and then 1/2 of the square root of x squared plus x, and then plus 1, then dx. So let's do our u sub. Let's suppose we let u equals x plus 1/2. So my mistake, I was supposed to write after completing the square. So let's do our u sub. We'll let u equals x plus 1/2. So that means du is simply just going to equal to just dx. So with that being the case, so this is pretty simple from there, that you can actually replace all of this. So I have 1 divided by square root of 2, and then we have our new bounds. If I just plug in 1/2, that's just going to be 1. If I plug in negative 1/2, that's going to be 0. And then put this back, so I have the square root of u squared, and then plus 3 divided by 4. So, and then du. So this actually looks a little difficult on how we can evaluate such integral. Well, this is actually going to have to utilize yet another u substitution. What we're going to do here is, this is actually going to be a little bit difficult, and probably in the most interesting and elegant way, such that, as I mentioned, we're utilizing the hyperbolic trig functions. So with that being the case, so why don't we suppose that in this case, we're going to let u equals the square root of 3 divided by 2 multiplied by the hyperbolic sine of x. So then du is then going to equal to just the square root of 3 divided by 2, then the hyperbolic cosine of x, and then dx. Okay, so now plugging all this back in, so now our new integral that's rewritten. So if I plug in 0 for over here, this is still going to be 0. And then if I plug in 1 for over here, so that means you just apply the algebra. So what we're going to have is the inverse hyperbolic sine. So let me first write that out, of 2 divided by the square root of 3. And then now to, of course, put in that substitution back. So now let's actually take things one step at a time. So I have the square root of u squared. So let's plug that back in, the square root of 3 divided by 2, and then the hyperbolic sine of x. So that's quantity squared plus 3 over 4. And then we multiply with our substitution over here. So of the du differential, it's the square root of 3, and then divided by 2, and then hyperbolic cosine of x, and then dx. So if we just simply reduce this down, then I have 1 divided by square root of 2, so let's see, 0. Hyperbolic, or inverse hyperbolic of 2 divided by square root of 3 is sine. If I simplify all this out, so what I'm going to do is I'll just write this out, and then I'll just erase it just to save some space. So what we have is 3, and then hyperbolic sine square of x, and then plus 3 divided by 4 if you expand this over here. And then add this with 3 over 4, I already put that down. So that being the case, so okay, there we go. And then now, if we actually reduce this down, I can factor out a 3, and so it's 3 times the hyperbolic sine square, and then plus 1, and that follows with the identity that's the same thing as equal to hyperbolic cosine square. So that means with that substitution, and then another thing to do is you can actually factor out the 3 divided by 4 of that radical. So that means I have the square root of 3 divided by 2 factor out outside of that. And because I also have that too, so that can also factor out outside of our integral as well. So we'll reduce all this down. So that means, let me put this back over here. So what we have so far is the square root of 3 divided by 2. And then you take that square root yet again. So that means that's actually just hyperbolic cosine, and then you just multiply with the hyperbolic cosine over here. So that means this is just hyperbolic cosine square of x, and then multiply with yet again the square root of 3 divided by 2 dx. But also, as I mentioned, factor out these constants, and so we have that this is actually just going to be 3, then multiply, or 3 divided by 4 times the square root of 2, multiply with the integral from 0 to the inverse hyperbolic sine of 2 divided by square root of 3 of just hyperbolic cosine square of x, and then dx. All right, so with that being the case, so you can actually do the same similar argument over here. You're gonna get something of a similar fashion, just like this, except instead your bounds is gonna be from instead the inverse hyperbolic sine of negative 2 divided by square root of 3, and then going all the way up to 0. So now with that being the case, if you just take all this back, then substitute it back, and then you can just combine it together. So now everything over here is going to be in the following. So now I have 3 divided by 4 divided by, or times the square root of 2, and then now this is simply just going to equal 2. So another thing, so let me actually first write this out. So this is inverse hyperbolic of 2 divided by square root of 3, and then inverse hyperbolic sine of negative 2 divided by square root of 3 of just cosine square of x, and then dx. So that being the case, so there's an identity that we can actually use to make the simplification even more easier. So what we have is that this is actually follows that hyperbolic cosine square of x is simply just the same thing written as the double angle for hyperbolic cosine of 2x, and then add this with 1. So with that being the case, I can actually just multiply with 1/2. So not only that, so 1/2, that means I'll factor that outside. And so what that'll do is that just changes to just 3 divided by 8 times the square root of 2, then the same bounds. So I'll cut to the next clip afterwards. And then such that this is actually going to be hyperbolic cosine of 2x and then plus 1 and then dx. So with this being in mind, another thing we can do is that notice that this is actually an even function. So what that means is that I can actually break this up as a sort of a double. So in other words, this is actually just going to be in terms of twice the integral. So if I multiply that by 2 times that, so that means that's actually just going to reduce down to 4 times the square root of 2 on that denominator. And so therefore what we have now is so far that this is going to be 3 times 4 divided by the square root of 2 from the integral from 0. And because this is also a symmetric interval we're dealing with, that's why we can also apply that evenness of from 0 to hyperbole inverse sine of 2 divided by square root of 3 of just hyperbole cosine of 2x and then plus 1 and then dx. Okay, so this is what we have so far. So now let's continue further, and that we can actually yet provide another u substitution. So let me actually go back to over here, or right here is fine. So we're gonna let u equals 2x, and so du, of course, this is just gonna be 2 dx. In other words, that's just dx is gonna equal to 1/2 and du. So with that being the case, that we're just looking at this integral, of course. So I have the integral 1/2 and then multiply with the, we're not gonna change the new bounds, we're just gonna leave this as in terms of an indefinite integral. So of hyperbolic cosine of u and then du. And so that's the same thing written as over here. This is just 1/2 and then multiplied by hyperbolic sine of 2x. So what that is that we actually can use yet another identity to say that, let me actually switch to a different marker for this. We can use the identity over here to say that hyperbolic sine of 2x is the same thing as hyperbolic, or 2 times hyperbolic sine of x multiplied by hyperbolic cosine of x. And this is great that the 2's will cancel. And so what we have now is that so far this is actually going to yield us with just 3. So 3 divided by 4 times square root of 2. And then inside of our integral, we're going to have that this is just hyperbolic sine of x, and then multiply by hyperbolic cosine of x, and then just add the antiderivative 1, which is just x, so plus x, and then now integrate the bounds from hyperbolic sine, inverse hyperbolic sine of 2 divided by square root of 3, and then to 0. Okay, so here's the interesting thing. There's actually some interesting functions, well, not interesting functions, there's an interesting identity yielding for both the inverse hyperbolic sine and including for the hyperbolic cosine. So the identity, we have 2 identities. So we have that the inverse hyperbolic sine of x is the same thing written as ln of x plus the square root of x squared plus 1. And another one we have is that the hyperbolic cosine of the inverse hyperbolic sine of x is simply just the square root of x squared plus 1. What that yields is that this is actually going to yield us some interesting identity over here. So I think one thing's obvious, see that if I just plug in 0, whole thing's just going to be 0. So now we just have to plug in this term over here. So now plugging this in, I have 3 divided by 4 times square root of 2. So if I plug in the hyperbolic sine back onto here, so hyperbolic sine of the inverse hyperbolic sine just gets rid of itself. So it's just 2 times, or 2 divided by square root of 3. So then hyperbolic cosine of inverse hyperbolic sine of 2 divided by square root of 3. And then we just add this with the inverse hyperbolic sine of square root of 2 divided by 3 over here. So let me actually make some room over here. So let me get rid of this side over here. So now after performing all this, so we can actually just use these identity to put in the substitution. So now I have that I so far is going to be, so let's see, 3 divided by 4 times square root of 2. And so now we have, this is reduced to 2 divided by square root of 3. Then you do the math over here with the arithmetic. So that's going to yield us to just the square root of 7 and then divided by square root of 3. I just wrote it this way just so we can actually notice some things that just can cancel out. And then add this with the ln of 2 divided by square root of 3. And then add this with square root of 7 divided by square root of 3. And so we can actually reduce this back to over here to see that. So square root of 3 times square root of 3, That's going to be 3. So we cancel out 3 from numerator to denominator, and then a 2 from here. So 2 times square root of 2 on the denominator. So I have the square root of 7 and then divided by 2 times square root of 2. So now I'll just distribute this back into here, into the natural log. So plus 3 divided by 4 times square root of 2, and then the natural log of, so square root of 3 just stays as it is on the denominator. So 2 plus the square root of 7, and then divided by the square root of 3. And so therefore, our integrand or integral we're working with is the final answer over here. So there we have it, the final answer to 1 out of 5 of the integrals from the final round of the 2023 Integration B. So let me know what kind of other methods there are that you solve to get such an answer like this. So yeah, that's pretty cool if you ask me.